purpose of this video is to familiarize you with the rules pertaining to significant digits and how to manipulate numbers while being conscious of significant digits, and also to review, hopefully, scientific notation and the use of exponents, specifically powers of 10. So, significant digits, sig figs, two names for the same things. After you've gone through this video, you'll probably look back and be able to make sense out of these rules here. So consider a rather contrived example. Let's say you're, I don't know, in a helicopter over the ocean, looking down on one of these Nimitz-class aircraft carriers, and you try to estimate the length of this thing. And maybe because it's near a port, you have some point of reference, you can kind of gauge how long this thing is compared to, for instance, a football field. So I've stacked up some football fields here. And maybe in your estimation, let me grab a laser pointer here, a virtual laser pointer. Maybe in your estimation, this aircraft carrier is close to the combined length of 3 football fields. Like you're fairly certain it's not as long as 4, and it's definitely longer than 2. Well, we know that a football field, if you subtract the end zones, is 100 yards long. And going forward in this discussion, let's just not worry about the end zones here. Pretend they're not there so that we've got 100 yards stacked up next to another 100 yards. And I will use the letter L to denote the true length of this aircraft carrier. So it would be fair to say, based on this picture here, that the length is approximately 300 yards. Now, in the context of a lot of physical science applications or discussions in physical science, things you'd read in the textbook, for instance, the word or the number 300, you don't really need the approximate sign because the way the number is written is already telling you that the number is approximate. All we know from looking at this picture, a cursory look at the picture, is that it's definitely closer to 300 than it is to 400, and it's closer to 300 than it is to 200. So there's really only one so-called significant digit. We're not sure what these other 2 digits are, but we're very confident in this first digit. So up here in the corner, I'm emphasizing this statement that L equals 300 yards. What it tells us is, well, we're not really sure what the value of these last 2 digits are or is, but we know that it's not 200 yards long and it's not 400. Okay, yeah, so we would say that this number has 1 significant digit. Even though it's got 3 digits overall, the 3 and 2 zeros, those last 2 zeros, the trailing zeros, are not considered to be significant. So that's one rule to take note of. Trailing zeros usually are not significant. There are some exceptions to that. You know, if you hear me pausing, it's because this pesky control bar is in the way. Let me get this thing out of the way. Okay. Trailing zeros not counted as significant. They're kind of like placeholders in a way. They really just tell you the order of magnitude. I mean, 3 is the only digit we're really sure about, but if you just wrote down the number 3, then you're telling the reader that this aircraft carrier is 3 yards long. That's ridiculous. Of course, it's 300. So you need those zeros to at least let the person know that you're talking about hundreds of yards. Now, this is where it gets a little silly, because if you're actually observing this in a helicopter, you couldn't do this. But suppose you had this image in front of you and you wanted to do a better job of estimating the length of the aircraft carrier by comparing it to the football fields below. So observe that the left end is lined up very well with the first football field. And then I'm going to zoom in. You know, maybe you've got a photograph here that you can zoom in on. And now we have a better look at where the right end of the carrier falls on that last football field. So it seems pretty clear that it's closer to 300 plus 30 yards than it is to, for instance, 320. And it's also closer to 330 than it is to 340. Now, it may be difficult to tell if it's exactly 330. Maybe it's 329, maybe even 328. But we can be very confident about those first 2 digits. And that is why it's acceptable now to write this number. Instead of 300, we can be a little more specific and say 330. So we've specified the hundreds digit, and we've also specified the tens digit because we're confident that those numbers are accurate. That makes those numbers significant. The 3rd digit is still insignificant in that respect because we're not totally sure what that last digit is. So when you write down 330, what you're really telling the person reading that number is, you know it's not 320 and you know it's not 340. It's closer to 330 than it is to either of these. That is why these two digits are significant. So this number, 330, has two sig figs. The last zero is a trailing zero. It's not significant. Two sig figs. And like I just said, we really don't have enough information to be sure of that last digit. Now, suppose that you could zoom in even more and you found that it really was, 330 on the nose, so that you were confident about that third digit. If I look closely here, it's really not 331 and it's not 329. So this should be a significant digit. How are we supposed to represent to the reader that that zero is significant when the usual rule is that trailing zeros are not significant? I need to have some way of saying, hey, actually this zero does matter. If you try just sticking a decimal point at the end, that's confusing, right? Looks like the end of a sentence. I read the other day, I'll get back to the topic at hand very quickly here, but I read that they did some study recently and millennials, was that the age group? They find periods aggressive in text messages and emails. Like if you end a sentence with a period, it almost carries with it an angry tone. I just thought that was hilarious, but I kind of know what they mean. So here's one way to do that. You could use scientific notation. The normal custom is to always put the decimal place after the first digit in scientific notation. Not always, but that's what you should default to in this lab assignment that you've got. But by putting the decimal point there, see, it's understood that trailing zeros are significant if they come after a decimal point. So the rule would be that trailing zeros are not significant unless they come after a decimal point. That's the advantage of using this notation. So what does it mean? Times 10 to the second power. This is 10 raised to the second power. So I will review this for those of you who have forgotten or maybe never learned it. This means multiply by 10 twice. It's the same thing as 3.30 times 10 times 10. And I'm sure you do know that every time you multiply by 10, that has the effect of moving the decimal place 1 to the right. So if we move that decimal place 2 times to the right, we do end up back at 330. So that's a convenient way of emphasizing that this zero actually is significant. It's after the decimal point. So there's one exception to the rule that trailing zeros are not significant. They are significant if they come after a decimal point. Let's review some powers of 10 that are worth being familiar with. Any number, well, I shouldn't say any number because what about complex numbers, but most numbers raised to the 0 power are considered to be 1. We just take that to be 1. That's a little weird, but 10 to the first power just means 10. 10 squared, as we saw, is 10 times 10, and 10 cubed. You get the idea. Every time you multiply by 10, you pick up another 0. I think it's worth memorizing that 10 to the third is 1,000. Any power of 10 that's a multiple of 3 has a name, or at least the lower powers of 10 to the 20, 20, drawn a blank here, fourth, for instance. I don't think that has a name, but we're all familiar with these numbers. 10 to the sixth, if you multiply 10 by itself 6 times, that's 1 with 6 zeros after that. We call that a million. Then we've got a billion with the B, billions, and then we've got trillion. After that, the names get a little cumbersome. Speaking of trillions, let's take a look at a really big number and how we can use scientific notation to represent that number. So just today, this is September 1st, 2020. I pulled up the usdebtclock.org website. I think that's the URL. And whoa, it wasn't that long ago that this number was quite a bit lower. We're up to almost 27, let's see here. This is thousands, millions, billions, well, trillions. So almost $27 trillion. And these numbers are stagnant because this is a picture, but if you go to the website, all these numbers are rolling back fast. It's kind of terrifying to watch. If you have problems with anxiety, don't go there. That's not going to help you. Okay, I'm going to round this number to 3 sig figs. Remember, trailing zeros, unless there's a decimal place, trailing zeros are not significant. Hence why I said there's only 3 sig figs. You can look at this number and infer that it's 26.7 trillion, but it doesn't jump right out at you. There's so many zeros that you do have to take a moment to parse that. So it would be nicer if there was a clearer way to represent this number. That's the use of scientific notation, or the usefulness of scientific notation. So I'm going to choose to, instead of putting the decimal point after the first digit, which is what you should normally do, I'm putting it after the 6, because let's check. If I put it after the 6, you know, the actual decimal point is way over here, is it not, for the actual number we're talking about? But if I want to put it over here instead, I would then have to move it back 3, 6, 9, 12 times. And the reason I chose to do that is because 10 to the 12th, that's one of those multiples of 3. We know that's a trillion. So it's easy to recognize that this means 26.7 trillion US dollars. If you were to use the usual rule where you put the decimal point after the first digit, you'd have this. And this is not quite as easy to interpret because 10 to the 13th doesn't have a number that we're all familiar with, or excuse me, a name. Either one works though. All right, so now you've seen a couple of the rules for deciding how many sig figs a number has, depending on how it's written. Now let's look at how to add and subtract numbers, bearing in mind rules about significant digits. So we're going to be conscious of sig figs while we add and subtract numbers. And actually, there's some pretty useful examples here. You can come back and look at this once you understand the concepts here. So I made up another contrived example. Let's say astronomers have been studying a particular spiral galaxy. This is an actual image. Is this the Milky Way? Could this be the Milky Way? Well, if it is the Milky Way, somebody took a really long trip to get out there and turn around and take a picture of our home galaxy, if possible. In any case, astronomers, they look at all the light coming from faraway galaxies. And because they know so much about stars and how luminous a star is based on its mass and temperature, things like that, they can estimate the number of stars in a galaxy based on all the light coming from the galaxy. There's other information I'm sure that they use as well, but so it's going to be an approximate count, of course. They can't actually go to the galaxy and count all of those stars individually for a lot of reasons. Number one, there's not enough time in your life to count that many stars. And there's also not enough time in your life to get to the galaxy, not even close. So those numbers are going to be approximate. And let's say that they came up with a number like 180 billion stars. And that's a legitimate number because I believe our own galaxy is estimated to have around 200 billion stars. And a lot of what you're seeing here is in the foreground. Like if you see these spikes, that's actually a star that's way closer to the telescope taking this picture than the galaxy is itself. So this galaxy is real far away. This is kind of like looking at a mountain from behind your driver's wheel. And then this is like a raindrop stuck on the windshield. It's way closer. So again, I'm just making this up, but suppose that one of these blobs over here was originally thought to be like a nearby star. And then they realized, oh, it's actually a globular cluster, which you'll learn about in your astronomy class. It's a globular cluster that belongs to the galaxy. So now we have to recount the number of stars, right? Maybe they want to revise their estimate for the number of stars because they just realized that this little cluster of stars belongs to the galaxy. And by the way, up here you see that I expressed this in scientific notation, right? 3, 6, 9 zeros. Oh, I did that wrong, didn't I? That's supposed to say 180 billion. So let me fix that before you get upset with me. Much better. Okay, so I looked up the number of stars that you can typically find in a globular cluster. It could be anywhere between 100,000 and a million, approximately. So let's pick a number like 300,000. Perhaps these astronomers, by studying the globular cluster carefully, they come to the conclusion that cluster has something like 300,000 stars in it. And so now the total tally for the number of stars in this entire galaxy, if you're going to include the number of stars in the globular cluster, presumably would just be the sum of these two numbers. Take the original estimate, add in the number that we've now determined is in the cluster, and that would suggest that the total number of stars is now 180 billion and 300,000. Now, is that reasonable to state? Is it even worth making this correction. Let's look at why that's really not advisable. That's because when you write down 180 billion, remember, trailing zeros, unless there's a decimal point in there, excuse me, trailing zeros are not significant. So when you write down 180 billion, all you're really saying is that you know the number of stars is closer to 180 billion than it is to 190 billion or to 170 billion. So roughly speaking, you can put it in this range, right? Because if the actual value was lower than 175, like if it was 173 billion, you would have written down 170, not 180. Okay, so if this is actually a possible value for the number of stars in the galaxy without the cluster, and this is also a possible number for the stars in the galaxy without the cluster, then there's a huge range of possible values still, even after you add in the 300,000. So let's go ahead and add 300,000 to that range. And now I would find that my lower limit could be 175 billion and 300,000. My upper limit could be 185 billion and 300,000. You see that? Since the first number with only 2 sig figs has so much uncertainty in it already, then there's no point in adding this 300,000 to the number. It would be silly to write this. When you write this number, you're telling the reader that you actually know the number of stars all the way out to this digit, which is much more precise than only knowing it out to this digit. Now, I was going to save this rule for the end, but I may as well tell you now. Zeros that are sandwiched between non-zero digits are significant. These are significant digits. So we've actually got 1, 2, 3, 4, 5, 6. The way this number is written suggests that it has 7 significant digits. But obviously, these digits are not really significant because we don't even know this digit, right? The total number of stars in the galaxy plus the cluster could actually be this number, where there's a 7 here, not an 8. So this is where we arrive at the rule for being conscious of significant digits when you're adding. And usually this rule is presented for numbers with decimal places. And I'm talking about it for numbers that don't even have a decimal point. So I try to come up with a way of wording this myself. Here's the rule for adding and subtracting numbers. Keep only the digits that have the highest significant place values that the two numbers have in common. I don't know how clear that is, so let's look at this example again. If I add these two numbers and I've lined them up so that the ones line up and the tens digits line up, etc., even though the number starts in the 100,000th place for 300,000, the zeros here are implied. We know what the digits are in the, for instance, the 100 millionth place and the 100 billionth place. They're all zeros. So we can say that these two numbers have these two place values in common. How do I word this clearly? I can say that these two numbers do not both have a sig fig in this place value. Definitely not. The first number, 180 billion, does not have a significant digit in the 100,000th place, 100,000th place, even though 300,000 does have a significant digits there. So since they don't share a significant digit there, I have to go all the way back to here. I can only keep these two. Notice I'm going towards the highest possible place value that they have in common. And like I said, this rule is not normally discussed with whole numbers like this. It's usually for decimals, and we'll look at an example of that in a second. But you can go ahead and add those zeros in there to make that rule easier to remember. Right, so I'm only going to keep those first two digits. There's no point in keeping this digit, again, because first number doesn't have a sig fig in that place value. You could say, I'll put it this way, you could say that both of these numbers have sig figs in the 100 billions place and the 10 billions place. Now the 300,000 happens to have a 0 in both of those places. Okay. This one's a little easier. This is normally how it's presented. If you're, and the rule doesn't have to apply to just two numbers. You could be adding and or subtracting a whole bunch of numbers. After you've added them together the usual way that you learned, you're not going to keep all these decimal places. Only retain the decimal places that are held in common by all three numbers. So every one of these numbers has a sig fig in the tenths place. So it's okay to keep a digit in the tenths place. And see how we have to round the 9, we'll turn the 8 into a 9. It's not okay to keep all three digits because the second number, for instance, doesn't even have a sig fig in the hundredths place, much less the thousandths place. So we don't actually know what the sum of these numbers is out to the thousandths place. We don't have that kind of precision. So there's really no difference between this example and this example, but this is the way it's almost always discussed because the decimal point makes it easier to talk about. And I think your homework assignment has mostly this sort of example anyway. So if you're adding or subtracting, do the addition the way you normally would, and then round so that you're only keeping the lowest number of decimal places held by any of the input numbers. Right? Keep the lowest number of decimal places. That's for adding or subtracting. Multiplication and division works a little differently. Here's the rule right up front. After you've multiplied or divided, and this is true of multiplication of 2 numbers, 3 numbers, any number of numbers, you just keep the least number of sig figs that any of those input numbers have. So if every number has 10 sig figs except for one of the numbers, it's only got 2. Well, then at the end, you're only going to keep 2 sig figs. Let's look at why. So as a silly example, again, consider an asteroid flying through space. Let's say astronomers have been studying an asteroid and they've been making measurements of the properties of this asteroid. So maybe they put a probe in orbit around the asteroid, and that's been done. If you think that's science fiction, that's been done a number of times now. And here's a pretty typical mass for an asteroid. This says 73 billion kilograms. A kilogram is the mass of 1 liter of water. That's a very familiar unit. So mass is just how much stuff a thing is made out of. It's not quite the same as weight because you have a certain amount of mass that doesn't change even if you go to the moon. Your body still has the same amount of stuff, but you're going to weigh less on the moon. So mass is independent of the gravity field. And you'll notice that this number only has 2 sig figs. We don't count the 9 zeros here because they're trailing. And I chose that rather imprecise number because it's difficult to determine the mass of an asteroid. You can't go out there and weigh it. You can't stick a scale underneath it. It would just fall towards the asteroid. That's kind of strange to think about. If you could somehow determine exactly what material it's made out of and make careful measurements of its volume, then you could use a computer to calculate its mass, but we don't have all that information. So that's why I went with 2 sig figs. Now, as far as determining the speed of this thing, you can do things like bounce radar off of it, just like they do with the way police can figure out if you're speeding with a radar gun. So let's assume that we've made a much more precise measurement of the speed. We've got 4 sig figs here, and the units are in kilometers per second. So in physics, there's a quantity we deal with often called momentum. I don't know why, but it's universal to use the letter P for momentum. And the momentum of an object is its mass times its speed. Faster something moves, and the more massive it is, the greater its momentum. So let's calculate the momentum of this asteroid based on the 2 pieces of information that we have. So you could just naively punch these numbers into the calculator. And something I'll have to talk about later is exactly how to use your calculator to deal with powers of 10, because you all have different calculators, but I'll do an example in a future video. This is the number I get when I punch all those numbers in. This is what the calculator told me. Should I keep all of these digits? First of all, how many sig figs are there? We don't count trailing zeros. Now, maybe you're thinking, wait a minute, there's a decimal place or decimal point here, so we should keep the sig figs, right? Well, not if they're written, or excuse me, I was going to say, since these zeros come after a decimal point, maybe you're thinking we should keep them, because remember the rule, trailing zeros don't count unless they're after a decimal point. But check it out, they're not really after a decimal point, are they? Because when you actually move this decimal point, 9 times to the right, well, then now those zeros become trailing zeros. So you don't count these. We've got 1, 2, 3, 4, 5, 6 sig figs. Should we really keep 6 significant digits in our answer if one of our input numbers only has 2 sig figs and the other one only has 4? So neither of these input numbers has 6 significant digits. Well, let's look at, again, at the mass here. When you write down the number 73 billion kilograms, you're really saying, you know it's closer to 73 than it is to 72. So it's not 72 and it's not 74. It's closer to 73. So here's a reasonable range. It's going to be between 72 and a half and 73 and a half. Well, if the actual mass of this asteroid were 72 and a half and not 73 billion kilograms, let's take that mass, the lower likely range, or the lower likely value in the range, and multiply that by this more precise speed and see what the momentum would be. If this is actually the mass moving at this speed, then the momentum would be this number, 1627, not 1638. And if the true mass of this asteroid was actually on the higher end, 73 and a half, moving at this precise speed, then it would actually have this much momentum. So both of these momentums are likely values. They're both possible because we're not exactly sure what the mass is. Since we don't know exactly what the mass is, there's a range of possible values for the mass, and that means there's a range of possible values for the momentum. Now think about it. If the momentum could be this number, and it could be this number, is there any point in writing all these digits? Of course not. We're not even sure what this third digit is, because it could be a 2, could be as low as 2, and it could be as high as 5. So there's not even really any point in writing down a 3. There's definitely no point in writing down this 5. We don't know the first thing about what the momentum is all the way out to the hundredths digit. So I think you're seeing why it only makes sense to keep the first 2 digits. We can only justify the 1 and the 6 because we're not even sure what that 3 or what that third digit is. Could be a 3, could be as low as 2, could be as high as 5. And hence the rule, only keep 2 sig figs. And notice we've got 2 sig figs in that number. So that's not a coincidence. There's a reason for that rule. Multiplying 22.45 by 73, this is not the number that showed up on my calculator, but it's the number I'm going to write down because these are the only 2 digits I can be sure of since I'm only sure of 73. I don't know if it's 73.642 or what, okay? So since one of the numbers only has 2 sig figs, it doesn't matter how many sig figs we have here, I'm just gonna stick with 2 sig figs in the output. That is the rule for significant digits when it comes to multiplying. It works the same way for division. You can try it if you want. You can pick an example like this and show that it works. Let's say something else about scientific notation here. We used it to express an extraordinarily large number like the US debt. Let's talk now about really small numbers and how to use scientific notation to express small numbers. So hopefully you remember that 10 raised to the -1 power. That sounds mysterious at first. What it means is raise 10 to the first power and then just take the reciprocal. So that minus sign means put the 10 to the first in the denominator. 1 over 10 or 1/10, we can write that as a decimal fraction like that. 3 different ways of writing the same number. So if we continue there, 10 to the -2 would be 1 over 10 squared. Well, 1/100th is written this way. Here's 1,000th, and so on. So some useful ones would be 10 to the -6th. Notice the ones digit here is in the 10th, 100th, 1,000th, 10,000th, 100,000th, millionth. It's in the millionth place because 10 to the -6th is 1 over 10 to the 6th. That's 1 millionth. Here we've got a billionth, and this is a trillionth. And there are prefixes, there are words for this, like if you're talking about distance, if you were talking about a millionth of a meter, you would call it a micrometer or micrometer. A billionth would be a nanometer. If you've heard about nanotechnology, that's technology where things are constructed on the scale of a nanometer. That's really small. That's almost as small as an atom. And then what's this called? This is a picometer, which I think sounds cute, pico. After that, there's femtometer. I don't know any of the words after that, but those numbers actually do show up quite a bit in chemistry and physics. Okay, so another dumb example. Let's see if we can express the speed at which your hair grows in miles per hour. Is that going to be a really big number or a really small number? Does your hair grow even 1 mile per hour? That'd be amazing if your hair could do that. Now I'm just in a reverie contemplating what life would be like if your hair grew that fast. It would be gross. Let's actually calculate that number, because you can Google this, maybe you know, your hair grows something like 1/2 inch per month. 1/2 inch. You know, since the lockdown, I have not got my hair cut. Let's see, we've been locked down for 6 months at least. 6 times 1/2, so 3 inches. My hair's way longer than that. I guess I stopped getting my hair cut before the pandemic. Okay, what I've done here is multiple conversions all at once. And I really should say more about this. You have a problem in this first lab where you have to do something like this. So this example serves two purposes. We can look at how to use scientific notation for small numbers, and we can also look at how to convert things. Would you agree that 1 foot is the same thing as 12 inches? Those are equivalent. So I'm really dividing a quantity by itself. That's kind of like 6 divided by 6, for instance. Well, 6 divided by 6 is 1. So what I'm really doing here is multiplying by 1. And that means I'm not changing the rate. 1/2 inch per month times 1 is still 1/2 inch per month. I haven't changed the value of that number or that quantity. Same thing over here. A mile is the same thing as 5,280 feet. So this quantity is really the number 1. Something divided by itself is 1. So each time I'm multiplying by 1, that means I'm not changing the quantity. I'm just converting it. I'm putting it into a different form. Maybe that's a challenging idea if you haven't been acquainted with it yet, but I've been careful to arrange all these conversion factors so that the units I don't want go away and the units that I do want come out of the expression. So I would like the speed of hair growth in miles per hour, not inches per month. So the first thing I do is I get rid of the inches. See how the inches are in the numerator and in the denominator? And you could cross those inches out as if they were variables in algebra. Inches will go away, feet will come out. Well, I don't want feet either, so I convert from feet into miles. So these two conversion factors together will turn inches into miles. And you can see I'm dividing by 12 and dividing by 5280, so that's going to bring my number 1/2 way down. Obviously, the hair doesn't grow at 1/2 mile per hour. It's going to be some number way smaller than that. Then we need to convert the time units. I would like to express time in hours, not months. So first, see how the months here, we'll cancel the months here. First, I'll convert my time into days, and then I'll convert my days into hours. All right, so 4 conversion factors. Altogether, they accomplish what I want. So this first slide here is showing the conversion of distance from inches to miles, and then we convert time from months into hours. Then you just put all those numbers into the calculator. You may be able to reason through this without even needing this equation that I've written. You know, maybe you can just use common sense, like, well, if it grows 1/2 inch in a month, then it's going to grow 1/30 of that in a day, and just continue in that manner until you've taken care of all the conversions. But if you have to do multiple conversions within the same calculation, it gets a little difficult to keep that all in your head. So it's nice to write it down. Here's the number I get. A whole bunch of zeros, 11 miles per hour. We knew it was going to be a small number. I'm a little shocked at just how small it is. This is not very informative, right? It's weird to look at. I mean, how many zeros are there? I can't even tell immediately. I have to actually count them. So it would be better to write it like this. So here's what I did. This is the opposite of what we did just a moment ago. The actual decimal place is here. This is where it is. But for a moment, you can pretend that you've got the decimal place here after the first digit, remember. How many times would you have to scoot this decimal point to the left to get it back to where it really is? Well, if you put it here, you'd have to go 1, 2, 3, 4, 5, 6, 7, 8 times to the left. And that means divide by 10 8 times. Or in other words, multiply by 10 to the negative 8th. This is a lot easier to look at, right? This means the same as that. Now, something that should help you when you're doing this lab, if you want to go backwards, like here we went from regular decimal notation to scientific notation. But what if it was the other way around? What if you had been given this number and asked to write it as a decimal without any power of 10? First, you have to move the decimal once to the left to get it in front of the digits. You've already used up one of your inverse powers of 10. So there's 7 left, are there not? So after you use up the first 0 to get to the left of your digits, you've got 7 more. And that's why you would write 0.1, 2, 3, 4, 5, 6, 7 zeros, and then the remaining digits. So keep that in mind when you have to go from scientific notation for a number much less than 1 back to the regular decimal form. 2 more rules that you've actually already seen. What's with me in human hair today? I happen to know that this is an average value, but the thickness of many people's hair is something like 50 micrometers. That's a millionth of a meter, So 50 millionths of a meter. So I've written it like this. Notice 1, 2, 3, 4, 5, 6. That 0, this 0 right here, is in the millionths place. Do we count those zeros as significant? No, because when you state the number 50, well, we already know that that's really just 1 sig fig, right? This is a trailing 0. That's really just 1 sig fig. So when you express this in meters, it's a really, really small number. You have to add in those zeros to indicate that we're in the millionths place. That doesn't make the zeros significant. They're just really placeholders. They're just there to tell you that you're talking about millionths and not thousandths or millions. They're just placeholders. Right? Just think about the original number. It's clear that there are not 6 sig figs in this number. So the rule is leading zeros, not significant. Now, what about this trailing 0 here? If you choose to write it after the decimal point, that indicates that it is significant. Remember the rule? Trailing zeros are significant if they come after a decimal place. Here, there's no decimal point. So if I were to interpret this, I would say it's just got 1 sig fig. Here, I would say it's got 2 sig figs. So if I wanted to write this correctly to re-express this number, I actually wouldn't put this 0 at all. I would just leave it at 5 to indicate that there's only 1 sig fig. If I did write the 0, that means that this 0 was significant. Okay, that's probably more than you ever wanted to know about sig figs. We'll use this a little bit through the remainder of the semester. Last rule, you've already seen it. Zeros that are sandwiched between, who was just telling me the other day that the word sandwich comes from some guy named the Earl of Sandwich. Like before this Earl, people, they would like pick up the turkey meat, shove it in their mouth, eat it by itself. Then they'd stick a piece of bread in their mouth. They would eat everything separately. And he was like, no, I'm just going to stack it all in one nice little package and bite into the whole thing. Was this guy really the first person to think of that? You can look it up on Wikipedia, the Earl of Sandwich. It's a great name. But sandwiched zeros are significant. And that is the end of this presentation.